A carnival game involves 5 buckets, each containing 5 blue balls and 15 red balls. A player blindly selects a ball from each bucket and wins the game if they select at least 4 blue balls. Now let's think about that. For each bucket, the probability that they get a blue, well, that's 5 out of 20, or a quarter. And therefore the probability they get a red is 3 quarters. We're going to let x be the random variable, the number of blue balls selected. And we want to state the distribution of x, including its parameters. Well, we've got 5 buckets, so that constitutes 5 trials, and we have a constant probability of success. So that's going to be a binomial, 5 trials, and since we're talking about blue balls, the probability there is going to be a quarter. What is the probability of a player winning the game on any given attempt? Well, they win if they get at least 4 blue balls. So we're talking about the probability of x being greater than or equal to 4. So if we go interactive, distribution discrete binomial CDF, going from 4 to 5 with 5 trials and a probability of success of 0.25, we get 0.15625. We're now told that players are charged $2 for each attempt at the game and offered a $150 prize if they win the game. By providing appropriate numerical justification, explain why this is not a good idea for the carnival organisers. Well, the expected win would be 0.15625, that's the probability of winning, times the amount for winning. So that's going to be the last answer multiplied by 150, and that is $2.34. So the expected win is greater than the charge for playing. In other words, on average, they're going to lose 34 cents per game. An observer records the outcome of 100 consecutive games and determines the 90% and 95% confidence intervals for the proportion of wins P. The confidence intervals are shown here. Which of the intervals is the 95% confidence interval? A 95% CI is wider than a 90% confidence interval. That implies the 0.04, 0.16 is the 95% confidence interval. How many wins were observed out of the 100 games? Well, for this, let's just think about how a confidence interval is constructed. This would be P hat take away something, and this would be P hat add the same thing. So the actual observed wins would be at the center of the interval. So if we do 0.04, add 0.16 and divide that by 2, so that 0.2 divided by 2 is 0.1. 0.1 was the proportion of winning games. If there were 100 games, multiply that by 100, and we must have won 10 games. So 10 out of 100 giving us that proportion. Determine what you would expect to happen to the width of the confidence interval if 400 games had been observed. So the width would halve. Now, why would that happen? Well, think about the calculation of the margin of error E. It has on the bottom here n. So in the calculation, you would end up with root p 1 minus p over root 100 for 100 games, and you'd have root p 1 minus p over root 400. And we know that that is 10 and that is 20. So therefore you get half of the width. The true proportion of wins does not lie within either of the above confidence intervals. Does this suggest that a sampling error was made and justify your answer? Well, the short answer there is no, but you're not going to get both marks for that. You have to justify. And quite simply, a confidence interval is not guaranteed to contain the true proportion. After all, a 90% confidence interval is only expected to 90% of the time.